Well, I thought I'd do a little tutorial on how to do PID tuning from the depth. Um, it seems like there's quite a few people that want to know how exactly do you tune the PID, what does it do, why do I want to do it. Um, so we have a basic from the depth flying boat plane thing. As you can see, there's no it's just a simple aerial AI here with a flight card, and it's very wobbly. And that could be good if you want to, be sort of be able to avoid incoming fire. So that's a good thing. But if you wanted to fly absolutely straight, then you can with the PID block, and you can also use the PID block to sort of program in your own oscillations by sort of deliberately tuning it wrong. So the first step to doing that is, well, you need to make sure that your aircraft or plane or boat or whatever is able to drive by itself relatively well. So you don't want to be have a completely uncontrollable thing that you just say, oh, okay, here, do it for me. Yeah, it's not really going to do that. So what I'll do here is I'll just turn off the AI, and yeah, so you can see that this plane flies pretty well manually, and that's really what you want before you even start with any sort of controls tuning. You want to make sure your thing is actually controllable, and yeah, so this thing controls fairly well. So I'll turn the back on. Oh, no, let's not fly into the hill. Right, just avoid the hill. Yeah, we're good. So I'll just show you how to do the basic PIDs. I haven't really done anything with the general purpose PID, but I presume the principle is the same. So let's try doing it. So if you go into AI, PID is here. So you put the block it down. You can put it on the AI, next to the AI, or next to one of these AI connector blocks. I'm not sure if you can do it on a wireless thing or not. Oh, it's momentum again. Right. Oh, come on. Why you do this? Right. So let's start with looking at what's actually in here. So first thing you want to do is select what exactly you want to control. So in this case, let's look at aerial roll first. When you click on this, you immediately see some kind of confusing graph and numbers and all kinds of sliders and things. If you're used to, if you know something about PID, if you're used to use PID with the sort of generalized controller, then all the gain options are slightly different. Just a note for people who know what PID is. I'm actually used to the sort of generalized PID formulation where you have sort of individual gains rather than this one, which has kind of combined gain, and then you have integral times and derivative times. But the principle is the same. So the first thing you do is turn integral all the way up to the no limit. I'll explain what these do in a bit, but let's just start by looking at. So turn integral all the way to the no limit. Put d to 0. So we'll start only looking at the p gain. So what's p gain? Well, if you look at this graph, you have the green curve is our current roll angle. So it goes from 0 to 180. So right now it's not really rolling a whole lot, so that's good. But if you want to see how the system behaves when you give it an input, so let's command a 10-degree roll Not actually sure which way it is. Let's see what happens. Yeah, so that's a roll to the left. Yeah, there we go. So that's a roll to the left. Let's increase it a bit. So what we've done here is we've commanded, which is the red line. So that's your set point. It's basically that's what you want the system to do. So you want it to roll 28 degrees to the left. And the green one is the actual measured value of your roll angle, and it's going up and down because it's kind of unstable. And the P gain is basically it tries to correct the error between the difference between the blue and the green by applying a command to the roll of the aircraft, trying to oppose that value. So the bigger the error, the more control it has. So it acts kind of like a spring, if you think about it. So the more you push on the spring, the more force it applies, and the gain here is basically how strong the spring is. So if you have a large error, you'll apply a large force, and when there's no error, then this applies no force. So in this case, it's kind of doing what you want already with just the default values. And for most things in this game, you don't really need anything else. The default damping in the physics engine itself by itself is more or less good enough for the damping. You might want some damping to slow things down a bit, as we will see when we go to the pitch. So it's oscillating here, you can see, and you don't really want that as for a perfect controller. You don't want that, and we'll see it more clearly when we do another. So switch to stimulus 2, which is set to 0. So we just told it to go from 28 degrees to 0, and you can see that it goes past 0 and back up again and oscillates around 0. So this is called the overshoot, and that's something you want to avoid if you want a good control algorithm. So if you switch it back and forth like this, and this is what's called a step test. So you can see it overshoots and it comes back in. So if you want to avoid the overshoot, then you can reduce the gain. As you reduce the gain, less force is applied, less control output is applied. The control output is the blue thing. So you can see when there's a large difference between the set point and the actual measured variable, there's a large input, and there's a small difference, there's a small input. So you want to tune this value such that those two, you get a reasonable control response without huge overshoot. In this case, we do have quite a bit of overshoot, but the oscillation is almost gone. So there's a trade-off. If you have a high gain, then the system will respond faster. So if we turn this up, it'll respond faster, but you have a bigger overshoot, and you have more sort of oscillations. So to reduce the oscillations, you can use the derivative control. So derivative control is kind of like a damping. What it does is it looks at the speed of change of the your roll angle. So if it sees as a big, so if you're moving, your roll angle is changing really fast, it'll apply a control to oppose that. So it basically, if you only had derivative control, your plane will basically roll very slowly, or not roll at all, because it's trying to basically remove any kind of rate of roll. So if we turn this up, you can see immediately we've dumped out the oscillation in roll, and now we're getting a pretty decent control. So now if we go back to stimulus 2 again, and you can see the control moves smoothly from one set point to the next set point, and we can in fact move this to like You can see, so you have these spikes when you have too much damping. You might think, well, if I just turn up the damping, then everything will just be stable. But actually, no, because this derivative actually amplifies so that any kind of tiny little changes, sometimes even the numerical errors of the simulation will get amplified. So you end up with a really noisy control. So you don't want to turn this up too much. You want it just enough to damp out the oscillations without having a noisy graph, and that will give you a reasonable control. So right now we have a pretty good roll control. Maybe a bit slow. So you can see now it goes smoothly from one to the other, with no overshoot and no huge oscillations. And if you want to make it go faster, if you want to roll from here to here faster, you can increase the gain. Let's try that. And you can see when I do that, it's adding noise now, because in the way this is formulated, this gain actually applies to integral and derivative as well. So when you increase the P gain, the integral gain and the derivative gain are also increased. So that's a bit of a trap if you're not used to this way of thinking. And I see there's a mountain ahead of us, so let's avoid that. Yeah. Alright, fine. So yeah, so in this case, we can do some more of this. And yeah, that's pretty reasonable. In fact, in this case, it's probably too much damping. That's actually slowing down our roll response. So we turn this down a little bit. Let's try this again. You can see this is now faster. We can make it even faster by turning down D more. And you can see we've turned the gain up so much that it's actually the control force goes to saturation. So it's basically it can't make it roll any faster because it's demanded the full roll response. And yeah, so that's more or less good. You can make it faster and make it slower, and that's up to you. You can turn up the gain. If you can accept a little bit of overshoot, you can turn up the gain even more. And it'll make your airplane roll faster or slower. Oh, in this case, we turn it up too much now. You can see we're getting this noisy stuff. So that's way too much gain. So you want your gain to be to get the perfect response. You want your gain to be just enough before you get this crappy stuff, and then you have the best response possible without any oscillations. So that's good enough for the roll. Let's do the pitch. So same thing, we set it to pitch. Play down test stimulus 1. Now this aircraft is much slower in pitch than it is in roll, so you have to bear that in mind. So it depends on what your airplane is like, or your boat or whatever it's like. Again, we turn the integral to no limit, so basically that turns off integral. Don't really need it most of the time, but yeah, I'll explain what it does in a bit. Let's just put a little bit of pitch so we're not crashing into the ground. Alright, let's say 7 degrees. So same thing again. We'll increase. I'll turn this to 0 and increase the gain. And 2 are green and red are more or less in the same region. When you're testing pitch, you have to make sure you don't fly too high into space, and then you have problems. Yeah, so you can see that's more or less good, and you have oscillations, so that means we can turn up the D gain to dampen that out. And yep, that's actually too much now. Don't need much. So oh, go up, go up. Right, so you see here the green and the red is kind of there, but it's not quite matching. So that's called a steady state error. So that error is always going to be there. So you never, with just the P gain and D gain, it is possible for the system to never quite reach the set point. So there's a slight error. You can reduce that error by turning up the P gain, or you can also use what's called the integral time. So basically, what integral gain does is it basically it sums up the area under the curve between the red and the green. So as you can imagine, the longer time it goes by with this error there, the bigger the integral will be. So let's see what happens if we turn down the integral. You can see the integral gain, which is the white line, is going up. So it's adding an additional input into our system. Give it even more. You can see now the green line is getting closer. So the integral gain gets rid of your steady state error, so it gives you so it allows you to match your set point exactly. Most of the time in this game you don't really need it, but you know, it's there if you do. So let's see how this performs. It's actually already pretty good. Yeah, so when I go from up to down, the steady state error is actually quite large. And but it will eventually go away because of our integral correction here. If you want to make it go away faster, you can turn up that gain. But again, like any of these things, if you turn it up too much of a good thing typically ends up with oscillating control inputs, and everything goes to unstable, which may be a good thing, because sometimes you want your aircraft to be a little bit unstable. Makes it hard to hit. Yeah, so that's pretty good. So I want to turn up the damping a little bit, so slows down the rate of pitch. Let's see how this works. Yeah, it's a little bit of overshoot, but yeah, more or less good enough. I mean, I would call that good enough. Yeah, let's call that good. So make sure you turn back to no stimulus once you're finished, otherwise your plane will be stuck doing circles and things. Right, so now if we go back to where the heck are we? If we give it a fleet move command, and it crashes into your plane. Yeah, for some reason fleet move doesn't seem to actually go to the correct altitude when you set a fleet move. Just to come back. Yeah, how do we test it? Let's add a Vanguard. change the AI so it actually does something. So now you can see the thing is flying straight on level, and rolls are crisp. No oscillations at all. So yeah, that's how you do that. We'll watch it do a attack run on this Vanguard. It's not really a great play. I made it in like half an hour, so basically just to test the PID control. I'm pretty happy that Netix managed to add PID. I mean, it's I don't think there's any other game out there that you can do PID tuning in. So, oh yeah, just one thing. So once you finish with this, so you might say, well, what good does it do me? I mean, it's just made my playing easier to hit because it's just flying straight and level. In fact, it's flying so straight, anything can hit it. Well, what you can do is just once it finishes the attack run, obviously flying stably makes your aiming a little easier, but it also makes you a better target. So let's just increase the pitch. And turn the derivative off and keep increasing it and increasing it. Now you see we're getting this pitch oscillation. Right, and you can see it's oscillating up and down. And most of that effect is coming from the integral. So the integral is going up, going down, going up, going down. And this is a slow up and down process that makes you quite a difficult target. Yeah, and you can tune exactly how much of this you want by tuning the gain. And of course you can do all the other stuff. The altitude stuff, I really could not get it to work properly. I mean, you can kind of get it to work, but it kind of, if you have pitch set on a different PID block, it kind of fights with it. I think that's what's going on. And it's also using pitch to control altitude, which is really not what you should do with airplanes. I thought you couldn't get. I thought yaw does nothing, but it turns out what you need to do is you need to set your AI to yaw instead of roll to turn. Basically, I'm sure everyone knows how to do that. Yeah, so that's it. Hopefully this video helps someone, and we'll see what Nick comes up with the updates of the game. Hopefully we could. What I would really like is thing that like ACB option to say periodically change the set point of your PID controller, so that you can say, for example, if I'm within 500 meters of an enemy, then periodically change my say pitch set point, so that you can sort of program in evasive maneuver, right? You can also do things like if say a missile is within 300 meters, so I want to do a full pull up, right? You could do like barrel roll, stuff like that. That'd be cool. But yeah, I'm sure he'll add it at some point, so it's pretty good at that. Yeah, and thanks for watching.